Welcome, listeners. So, here again we have gathered to discuss the next important topic, and possibly this is one of the most important topic in our series on series of lectures on fundamentals of geology. And I'm Dr. Shandi Banerjee, a faculty member in the Department of Geology, Varanasi in the University, Varanasi. So, we'll be looking at the constituent of what we see around us. Obviously, if you go to any mountains, or even if you go to a sea beach, for example, then you can see, obviously, in mountains you can see varieties of rocks that are making up the mountain, as well as if you go to a sea beach you can see sand, and the color of this sand also sometimes varies from place to place. If you are looking at the sand grains or the color of the sand along the coast of Bay of Bengal, or you are looking at the sands along the coast of Arabian Sea, then obviously there are some differences in between this sand. And also, so here also I would like to introduce the term mineral, that obviously the main constituent component of any rocks that we can see around us. And also, if you can remember from a few lectures before this particular lecture, when we discussed about the origin of the solar system, we talked about the differentiation of the earth and how the stratification of earth took place. There, if you can remember, broadly speaking, we have this peridotite bearing mantle. So obviously that is a rock, and peridotite also is composed of certain minerals. We'll look into that. Also, if you remember that the land or the continents that we have seen, that how the continents have formed, they are also composed of granitic rocks, and also the oceanic crust that is composed of your basaltic rocks. So each and every rock that we see around us is an assemblage or a combination of minerals. It could be a few minerals, it could be several minerals. So first we need to understand that how minerals form. So to start with, obviously I'll start with this term compounds that we all know from our school life. The substances composed of two or more elements which are chemically bonded together in a fixed proportion are generally referred to as compounds. So minerals are compounds formed by natural processes. So we can also develop compounds in our laboratory. We can generate compounds in means you can say artificially, but whenever we are talking about minerals, then obviously minerals are naturally occurring compounds. Apart from that, the composition of these compounds will determine the properties, as well as when we'll try to classify minerals, the composition is also an important parameter. Apart from that, these compounds, whenever a compound is forming, there are certain bonds. There are several types of bonds. We will be discussing that in a bit. And also, these types of bonds regulate the composition as well as the structure of the compounds. For example, if I look at some of the example, I can speak about compounds like water, sodium chloride, like means table salt that we use daily, and you can think about other compounds like carbon dioxide and calcium carbonate, and they also play an essential role in our daily lives, be it the table salt like that of NaCl, or for different natural processes also these compounds are involved, and definitely for industrial purpose and everyday life, we knowingly or unknowingly, we can say we use, or the compounds are intricately related with our daily life. So simple example, if I think of a quartz grain, that is, you can say also the main constituent of any sand, that is quartz. It's a compound formed from silicon and oxygen. So the composition of quartz is SiO2, that is also the chemical formula of quartz, and definitely that is also a compound. But when it is developing naturally, and it does generally, it always develops naturally, so your quartz is a mineral as well. Then whenever I am talking about a compound that is formed as a result of combination of sodium and chlorine, that is sodium chloride. So if it is forming in a natural way, then we can consider it under or refer it as a mineral, that is halite. Now specifically talking about minerals. So now we can define minerals are naturally occurring inorganic solids with a crystalline structure and definite chemical composition. So definitely you can say that it should have specific, because obviously it is also a compound, so it should have a specific chemical composition. Now if I want to break down this definition and go into further detail, then if I want to refer a substance as a mineral, then what are the criteria that are required to be satisfied before referring it as a mineral? So the first criteria is that always that it should be naturally occurring, then it should would have been developed through inorganic processes, generally speaking, and it is definitely a solid substance, and it should have reasonably definite crystal structure as well as reasonably definite chemical compositions. So again you can see this chemical composition, whatever elements are forming some compounds that will define a mineral, it should have a specific chemical composition, and likewise we will be talking about different crystal structure as well in a bit. So in that case as well, it should have a very well defined regular arrangement of, you can say, atoms or molecules that are arranged in a very regular manner. So that will define your crystal structure as well. So broadly there are two kinds of mineral if I want to classify in a very broad term. Then the first category is your crystalline minerals or crystalline substances, which will definitely show you ordered arrangement of atoms and molecules forming distinct crystals. We have talked about different crystals for different minerals in our previous lectures when we discussed about crystallography. So you can see that you need to have a very ordered arrangement of atoms and molecules such that they define or they develop distinct crystals. Then the other category is your amorphous minerals, which lack long range order arrangement of atoms and molecules. So in your amorphous minerals, what is happening that your atoms and molecules, they are arranged in a random manner. So these two diagrams you can see shows you the first one that represents the crystalline structure. You can see that there is a very regular arrangement of these molecules that are placed side by side. But in case of the amorphous minerals, you can see there is some randomness and it is not as regular as compared to that of the crystalline minerals. So you can say also that in case of your crystalline minerals, atoms vibrate in place in a fixed pattern. So you can see there is a fix here, it is kind of a hexagonal pattern that you can see. So they are fixed in space like this. But in case of your amorphous minerals, these atoms are not at all fixed in place. They are giving you a kind of a random arrangement. Then looking into some other examples, first of all, like I was mentioning, your table salt, that is sodium chloride, it forms also, the mineral is referred to as halite. So it also shows a very regular arrangement, you can say here, like this. So these are the molecules of, you can say, chlorine, and these the solid black ones are your molecules of your sodium. So they are arranged and bonded together in a very regular, though it is quite complex, but still I can say it's a very regular pattern or regular arrangement that you can see in case of halite mineral. Now if I also compare at the look that how your crystalline minerals will look, how your amorphous minerals will look, you can say that though quartz and obsidian, these are two different minerals, they have exactly same chemical composition, that is SiO2 or silica. So in case of quartz, which is giving you a crystalline appearance, you can see that the development of crystal is quite regular, as well as they are giving you a very clear, you can say, arrangement of faces and edges and apex, like that we have seen in case of the geometrical parameters of a crystal when we discussed about crystallography. Similarly, if I look at the obsidian with same composition, but here you can simply differentiate between this kind of development of crystal, which is very well developed and regular arrangement of crystal, here you would not be able to identify or separate any crystal from the rest of the obsidian. So here I can simply say that this one is a crystalline in form of silica, that is quartz, and this is an amorphous form of silica, that is obsidian. Now, before looking into mineral in totality, you should also know about the role of various elements. Obviously, we will not be talking about every element in the periodic table, but just to mention a few and their role, because these are, you can say, the most commonly occurring elements in any mineral, or you can say specifically rock forming minerals. That means the minerals which are dominantly responsible for formation of any rock. So to start with the first one, the hydrogen as an element. So definitely we all know that hydrogen is present in water molecules, and that is essential for mineral hydration and dissolution. It also plays a role in the formation of hydrothermal minerals like quartz and calcite, and as we know that it is also a very essential constituent of certain evaporites or evaporite materials like gypsum. So gypsum has a chemical formula of calcium sulfate with 2 water molecules. So definitely hydrogen is an important constituent in it. So hydrogen having an atomic number of 1, you can see, with 1 proton sitting at the center, surrounded by the equally negatively charged electron surrounding it. Similarly, the next important element that has a significant role to play in case of mainly sedimentary rocks, we will be also discussing about sedimentary rocks in a few lectures from now. So carbon forms obviously carbonate minerals such as calcite and dolomite. In dolomite, you have both calcium and magnesium that is combined with your carbonate, and through precipitation or sometimes obviously biological processes. Carbon also plays a significant role in the formation of organic minerals like coal and graphite, and it also participates in the formation of carbonates in hydrothermal processes. So carbon, you can see, has an atomic number of 6 with atomic mass of 12. Here also you have 6 protons and 6 neutrons that make up the atomic mass of 12 with the atomic number 6. So carbon, like hydrogen as well, carbon also play a significant role in the formation of various minerals. Then comes again possibly the most important one, that is oxygen, that commonly present in all oxides, silicates and sulfates. Means varieties of minerals will have definitely oxygen as a chemical constituent in it. So it also helps in your oxidation reactions involving oxygen that are crucial for the development of various minerals, and it combines with other elements very easily, and the most dominant one is the silicate minerals. It is actually the most important constituent of your silicate minerals, and also the that are the most abundant and group of minerals in the earth crust. Like we can see quartz, will be looking into feldspar as well. So if you remember quartz, again with a chemical composition of SiO2, that means your oxygen is getting combined with the silicon to form your mineral, that is quartz. And oxygen also, apart from its own presence, there are broadly 2 isotopes of oxygen that are also present in nature. The first one with an atomic mass of 17 with your 9 neutrons in it, and the second one with atomic mass of 18, which is also referred to as O18, with 10 neutrons within the atomic structure. And the normal one that we breathe into ourselves is with having an atomic number of 8 and atomic mass of 16. Then coming into the last one, obviously there are other elements which also play a significant role in the formation of the minerals, but looking at your iron, so iron forms a wide range of minerals including oxides, sulfides and silicates, and it plays a role in the coloration of minerals, like for example red color mineral that is hematite, and it is also important in the formation of clay minerals through your weathering processes. So iron again having and atomic number of 26 is also a very important constituent in any mineral. Now, taking into different elements and combining different elements, you can obviously create a compound, and likewise you can also say that by and combining several elements I can also create minerals. So the first type of bonding that is responsible for this combining of this, you can say, these elements, the first type or nature of bond that is found naturally is your ionic bond. So it forms between ions of opposite charges. For example, here again I'll take the example of your sodium chloride, your table salt NaCl. So sodium has a positive charge in its outer shell, like this one, with 1 electron here, and chlorine have again 7 electrons in its outer shell. So it will try to will be also talking about the octet rule at the later part of this lecture. So they will try to always form for individual shell, the first one or the first orbital will be always have a valency of 2, then followed by 8, and again it should have 8, but when it is not having a valency of 8, then in that case it tries to combine with some other element to complete its valencies. So that's why your ionic bonds develop. So your one atom loses electrons while the other gains electron. So you have also a strong electrostatic attraction between the ions that holds them together. Example, you can think of halite, like I mentioned. Also you can think of calcite with your calcium cation having a 2+ charge and your carbonate anion having a -2 charge. So these two also gets bonded very easily and they form calcium carbonate. That results also in the formation of a mineral, that is calcite. Then coming into covalent bond formed by the sharing of electron pairs between atoms, as you can see here that your electrons are getting shared like this. So the electrons are shared in such a way that each atom achieves a stable electron configuration, like I was referring to the octet rule that we will be discussing in a bit. So for example, again in case of carbon, you can say that each carbon atom forms strong covalent bonds with 4 other carbon atoms, resulting in a rigid crystalline structure. So this 4 is bonded with this one and they are also sharing the electrons in such a way that it is forming a very rigid and very strong regular arrangement. Similarly, other example is your quartz, like I was discussing silicon dioxide, where your silicon and oxygen atoms, they share electrons to form this covalent bond. Then also you have the van der Waals bond, which is relatively a weaker bond, but still it is sometimes it is essential to develop minerals like graphite and talc. So it is a weak intermolecular force that arises from the attraction between temporary dipoles, you can see here, in the non-polar molecules. It occurs due to fluctuations of electron distribution resulting in temporary charges when the distance between in these atoms are relatively small. So it is a kind of a bond that gets generated when you are in proximity to another atom. So in case of graphite, your layers of carbon atoms are held together by strong covalent bond, but within the layers they are attached due to this van der Waals forces. Then you have the next one, that is your metallic bond. So the metallic bonds are definitely, like the name suggests, they are found in metals, where your metal atoms pull their valence electrons like this one, M+, forming a sea of d localized electrons that are present in this sea, and these are your metal ion, which are kind of floating or which are surrounded by this delocalized electron. So your positive metal ions are surrounded by this electron sea, creating a strong attraction that holds the structure together. So the best example again of this metallic bond is gold. So your gold atoms form metallic bonds, resulting in its characteristic malleability and conductivity. Similarly, also for example, copper also exhibits metallic bonding, allowing it to conduct electricity and heat efficiently. Then obviously the most common one, that is your hydrogen bond that we also see in water. Definitely hydrogen bond like this are found between a hydrogen atom bounded to an electronegative atom. It could be oxygen, it could be nitrogen, sometimes fluorine as well, and another electronegative atom. So relatively weak compared to covalent or ionic bond, but important in various biological and chemical processes. So the most common example is obviously your water. In case of normal water, you can see that the hydrogen bonds are constantly breaking and they are reforming to bind the water molecules together. And here, in case of ice, they are forming a more stable and more regular arrangement that we can see here. Also, in case of hydrogen fluoride as well, hydrogen fluoride molecules are held together by the hydrogen bonds. So now looking at the different types of bond at minerals, there are some minerals as well like that of calcite, that is dominantly calcium carbonate, and also quartz. You can also see a combination of bonds that are present in that. It is not always that the one type of bond is only responsible for the development of one individual mineral. It is also possible that a combination of different bonds are responsible in the formation of a particular mineral. So, for example, if I look at calcite, you can see a beautiful calcite that has a very transparent to translucent kind of means you can say crystallinity in it. So, calcite may have predominantly ionic bonds, which is dominate 80% by the ionic bond, but it also possesses 20% of covalent character due to the partial sharing of electrons. So, you can see it is not necessary that a mineral will always have one type of bond. It might have a combination of 2 or 3 different kinds of bonds. Similarly, in case of quartz, which is just you can say a reverse of that of calcite, in case of quartz, it exhibits covalent bond, and that is the dominant bond in it. 80% is getting controlled by the covalent bond, and small portion of ionic character, about 20%, is also present in case of the crystals like this or quartz as a mineral. Now coming into the final rule of this, that how these elements are getting bonded, and finally how these bonds are getting controlled. This is governed by a rule, that is your octet rule. So it's obviously it is also a fundamental concept in chemistry, but we'll be looking into bonds specifically because we are dealing with the geological perspective of this idea. But just to introduce the concept, your atoms tend to gain, lose or share electrons that I was referring to in case of NaCl, that it is having orbitals that has valency of 2, 8 and then 8, but in case of sodium it is having a single electron in its last orbital, whereas in case of chlorine it is having 7 electrons it is in its outermost orbital. So that 7 and 1 electron, they will try to combine in such a way that they form the ionic bond between your sodium and chlorine, and finally forms the mineral, or it finally forms the compound, that is NaCl or sodium chloride. That will again result into the formation. If it is occurring naturally, it is giving you, means it is also occurring as a solid state, definitely it's a mineral, that is halite. So your atoms, again if I say the atoms tend to gain, lose or share electrons to achieve a stable configuration like this. You can see this example of 8 valence electrons, except for hydrogen and helium, which strive to have only 2 electrons in their outer orbital, also known as the rule of 8 or the noble gas configuration. So in case of noble gases, your outer shell has reached this 8 valency, so you don't need to bond it to any other element to create a new compound. So it is not necessarily important in case of your noble gas, because they already has reached this octet state. Now the relation of or the application of this octet rule to various ionic bonding, various kinds of bonding. The first one is your ionic bonding. The octet rule governs the formation of ionic compounds, like I was discussing about sodium chloride, where your atoms gain or lose electrons to achieve stable octet. So definitely it will then it will manage to develop a mineral as well. Then you also have its presence in covalent bonding, where your atoms share electrons to complete their valence shells adhering to the octet rule. So, you can see that octet always your elements will try to reach a stable configuration by following this octet state. Then it is also important for mineral stability, that minerals formed through these bonds that are involved between the atoms, those that adhere to the octet rule tend to be more stable. So, if the resultant mineral that is forming by the bonding between two or three elements in a specific condition. So, if by following this octet rule, or if the individual elements they reach the octet state, then obviously the mineral will be more stable in the mineral stability series as well. We will be also discussing about mineral stability series in a few lectures from now. Then also it is important in case of crystal lattice formation, the octet rule influences the arrangement of atoms, like we have seen that your electrons get shared, and that is why they can also contribute to the crystal lattice, and finally, so that your mineral reaches a stable configuration. And also it is important in case of chemical reactions in mineral formation processes, adherence to the octet rule guides the exchange and sharing of electrons. So, that means when two different elements or two different compounds, for instance, they are reacting with one another, then also they will always try to achieve this octet state, and that will also govern the stability of these compounds. Again, that is obviously we are also referring to minerals. That means if a compound is having a better stability or stable configuration, then it will result into more stability in the mineral stability series, as well as the reactions between these compounds will be complete and it will try to achieve a stable configuration. So, finally, before I end this discussion on formation of minerals, here you can see a naturally occurring diamond that you can see has developed into a crystalline nature. So, here again, it means if you can simply think about my first 2-3 slides, you can see the difference between an crystalline diamond and amorphous, sometimes amorphous graphite, which is also having a chemical composition of carbon. So, diamond is also having a chemical composition of carbon, your graphite is also having a chemical composition of carbon, but the bonds, the type of bonds involved in the formation of diamond is distinct from that of the type of bonds that are involved in the formation of graphite. Like for example, in case of graphite, we have this simple or weakest van der Waals forces of bonding. So, I like to conclude with this. Thank you for your patience.